Hello everyone, my name is Jason Gregerson, and this video is going to be Introduction to Row Reduction. So this video has three main goals. First, we're going to define what row echelon form is, or REF, sometimes called echelon form, and also define what reduced row echelon form is, or RREF. Next, we're going to formalize an algorithm for expressing a matrix in RREF. So we're going to find a way to take a matrix and put it into reduced row echelon form. And along the way, we're going to learn some important vocabulary that we'll see later in the course. So we'll start with our first definition. A matrix is in row echelon form, REF form, if all the non-zero rows are above any rows of all zeros, each leading entry of a row is in a column to the right of the leading entry of the row above it, and all the entries below a leading entry are zero. Now what in the world does all that mean? Well, let's take a look at an example. This first example, this matrix here, this is an example of a matrix that is in REF form. And so the first criteria says that all non-zero rows are above any rows of all zeros. So we have one row that has all zeros in it, and that needs to be at the bottom. And if it wasn't in the bottom, I could do a row interchange to put it at the bottom. The next one is the most confusing one. It says each leading entry of a row is in a column to the right of the leading entry of the row above it. So in other words, this leading entry must be to the right, in a column to the right of the column of the previous leading entry. And the result kind of gives us a staircase effect as we look at our leading entry values. So let me just mark all the leading entries. This is the leading entry of row 1, this is the leading entry of row 2, and this is the leading entry of row 3. And so as I move to the right, they go down rows. Now these leading entries are pretty important. In fact, the leading entries, the positions where these leading entries are in row echelon form, these are going to be called pivot positions. And the columns that have pivot positions are going to be called pivot columns. And a lot of the theorems that we're going to use later are going to be phrased in terms of pivot positions and pivot columns. So it's important to know what those things are. Now let's look at some examples of matrices that are not in REF form. So this first matrix is not in REF form. And so what we'd like to do is look at all three of these, identify why it's not in that form. So I would encourage you to pause the video at this point and just take a look at each matrix and write down the reason it's not in REF form. And then we'll take a look at them. This first matrix is not in REF form because it doesn't meet the first criteria. I have a all zero row and it's not at the bottom. So it's failing that first criteria. The second matrix, this one right here, is failing the second criteria. I have a leading entry here, and the second criteria says that it should be in a column to the right of the leading entry of the row above it. But the row above it has a leading entry here. And so this column is to the left of, not the right of that column. So that's why this one is not in REF form. And once again, a row interchange, if I interchange row 2 and 3, would probably fix this problem. And the last one is not satisfying the third criteria. It says all the entries below a leading entry, below the pivot position, must be 0. So I have a pivot position, all zeros below it. Pivot position, all zeros below it. Pivot position, not all zeros below it. And so because of this position, or because that value not being 0, this is not an REF form. Now what about RREF form, or reduced row echelon form? Well, a matrix is in reduced row echelon form if, well, first of all, it must satisfy all the conditions of row echelon form. That's what those first three are, the exact same conditions we just looked at. So not only must it satisfy all those, but it must satisfy two additional criteria. Number 4 says that the leading entry in each non-zero row is 1. And 5 says each leading 1 is the only non-zero entry in its column. So let's just look at some examples of these two extra criteria. So the first two are in RREF form. So all my leading entries, my pivot position values here, are all 1. Also, that next criteria says that each leading 1, each pivot position, is the only non-zero entry in its column. So not only must there be zeros below the pivot, but also above the pivot. That's this additional criteria. The second one is also in RREF form. I have a pivot position. In fact, that's the only row with a pivot position because the rest are to all 0 rows. but it has a pivot position, and all the values in that column are 0. 0 here and 0 here. And the leading entry is 1. So that one is an RREF. What about these next two that are not in row reduced echelon form? They're actually both in REF form. So they do satisfy those first three criteria, but they're not satisfying one of these last two extra pieces. So this first one, this is not in our REF form because here's my pivot position, here's that leading entry, and that value is not equal to 1. Now I could scale that row, and now it should fix this problem. In the second matrix, looks like I'm even missing a value here, so I'll put a value in right there. And that value specifically is the problem. That is why this is not in our REF form. For this to be in our REF form, this value would have to be 0, because not only must I have zeros below this pivot position, but also above it. So now that I know what REF and RREF are, how do I take a matrix and put it into one of these forms? And the next question should be why? Why would I put in these forms? So in general, what we're going to use this for is we're going to have systems of linear equations. And we're going to be able to write those systems as augmented matrices. And if we take those augmented matrices and we use row operations to put them into RREF form, we should be able to see the solutions for that linear system. So this process of taking a matrix and row reducing it is an important process. So let's see how we do it. So we have 5 steps here. And the first step says create a non-zero pivot position in the top left position. So here's my top left position, and I want to start with that as a pivot position. Now all I really need is for this to be a non-zero value. If there was a 0 in that position, and there were other non-zero values in that column, I would just do a row interchange to put a non-zero value there. So this one's already satisfied. I have a non-zero value there that I can use as my pivot position. So that's a check. Let's move on to the second one. It says use row replacement to create zeros below the pivot. So I need all the values below that pivot to be 0, and right now they're not. We use a row replacement. I'm going to take R2 and replace it with R2 minus 2 times R1. And if I do that row operation, well, I'm not changing the first row. I am changing the second row though. I'm taking row 2 minus 2 times R1. That will give me a 0 value here, 1 value here, a 1 value here, and a -2 value here. And now I'm not doing anything to the third row. And so using row replacement, I have created zeros below that first pivot. Now the next one just says repeat. So I've basically taken care of that first column, and now I'm going to look down. I use this first row. I've created a pivot, and I've eliminated I've created zeros below it. Now I'm going to go over here and find a pivot. So here I have this position, and there is a non-zero value there, so that will be my new pivot position. Once again, if there was a 0 there, and there was other non-zero values below that spot in this column, I would do a row interchange to make sure I have a non-zero value there. So that's going to be my new pivot, and now I want to use row replacement to create zeros below it. So I have to eliminate this -1. So the row operation I'm going to do here is let R3 equal R3 plus R2. And when I do that row operation, I get 0, 0, 2, and -1. And so that's me repeating. And I would continue to do that until I run out of rows. So now I've taken care of the first 2 rows. I look at this third row. I say here is my pivot position. And I've gotten to the bottom, so I don't have to worry about creating zeros below it. So really I'm done with this first stage of this algorithm. In fact, these first 3 steps, we're going to call the forward phase. The forward phase. And when I'm done with that forward phase, my matrix should be in REF form. So the forward phase ends with REF form. And to do that forward phase, once again, I just started with pivots, and I did row replacement to create zeros below the pivots. Now what? Now we'll start the backward phase. The backward phase just says begin with the rightmost pivot. So far, this is my rightmost pivot. And now I want to use row replacement to create zeros above the pivots. So it's kind of like I use the pivots, I created pivots, and I created zeros below them. And now I'm going to start on the right-hand side and work my way back up. So now I'm going to create zeros above these pivots. So to do that, I'm going to need to do another row operation. I'm going to take R2, and say R2, new R2 is R2 minus 1/2 R1. That's the operation I'm going to do here. R3 is going to stay the same. And this will be, see, 1 minus 1/2 of 0 is 1. 1 minus 1/2 of 2 is 0. And then I have negative 2 minus 1/2 of 1. So negative 2 plus 1/2 should be a negative 3/2. And then I haven't changed my first row at all. And once again, if I had a non-zero value here, I would do another row operation to create a 0 there. And then from here, I would look, so now I've taken this pivot position, I've created zeros above it. I would look at my next pivot position, create zeros above it. Once again, in this case, I'm kind of lucky because I already have zeros above that position. And then I go to my last pivot position, there are no values, so I'm really done at this point. And now my last step is to make sure all those pivot positions, all those leading entries have values of 1. So I'm just going to scale those pivots to have values of 1. To do that, I'm going to take R1 and say the new R1 is 1/2 of the old R1, and the same thing with row 3. I'm going to multiply that row by 1/2. The result will be 1, 0, 0, 1/2, 0, 1, 0, negative 3/2, 0, 0, 1, negative 1/2. As I finish this, and this last two steps here, we're going to call the backwards phase. The backward phase. And when I finish that phase, my matrix should now be an RREF. We can verify that it is. And once again, if you can visualize this now starting from a linear system and having this be some sort of augmented matrix, I could see my solutions directly from this. So that's the value that we're going to look at next time. For now, we've just used these 5 steps to take a matrix and put it into row-reduced echelon form. And as a last comment, I would encourage you now to go through your book and start trying some problems. Grab some matrices and see if you can take them and put them in RREF form. And that concludes this video. Thank you.